we're going to be talking about the activity series of metals and salts. This is a combination of a metal, which is going to be solid, plus a salt, which is going to be aqueous. And what happens is the metal combines with the anion from the salt, and the cation from the salt ends up by itself. This is a single replacement reaction where A plus BC produces AC plus B. So as an example, if I take aluminum, just a solid metal, and I add it to a salt that is, let's say, copper nitrate, copper 2 nitrate. So I have aluminum, which is A, copper, which is B, and nitrate, which is C. What's going to happen is the metal is going to take the anion away from the salt, and the cation in the salt will end up alone. So A is going to connect with C. So I'll work that out down here. I know that when aluminum becomes an ion, it takes on a +3 charge. Nitrate has a -1 charge, therefore my compound will look like that. So I'll write that over here, AlNO3, and that's aqueous. And the cation from the salt ends up alone, and if it ends up alone, it ends up as a solid metal. This is called a single replacement reaction. The reason why it's called a single replacement reaction is because a single metal is replacing another metal in aqueous solution, right here. Okay, so now that we have our equation, we need to balance the equation because according to the law of conservation of matter, what you put in, you have to get out. And so I have my reactants on the left side of the equation, aluminum plus copper 2 nitrate. And I have 1 aluminum here. If you look on the right, I have 1 aluminum. So that's good. On the left, I have 1 copper, and on the right, I have 1 copper. That's good. However, over here, I have 2 nitrates, 2 of this whole thing. And over here, I have 3 nitrates, so 3 of this entire thing. So the least common multiple between 2 and 3 is 6, and so what I'll do is I will put a 3 here and a 2 here. Move my arrow over. And so now you multiply them across, so now I have 3 times 2 is 6 nitrates, 2 times 3 is 6 nitrates, so those are now balanced. However, this 2 also distributes to my aluminum. Therefore, I need to put a 2 over in front of this aluminum, and this 3 distributes to my copper. Therefore, I would need to put a 3 over there in front of my copper. So that would be a balanced single replacement reaction in which a metal takes away the anion from an aqueous ionic compound in order to produce its own aqueous ionic compound, displacing that metal. Let me give you another example. Let's say that I have a piece of solid zinc and I put it into a silver nitrate solution. Leave spaces for balancing. It's going to produce A, B, C. A is going to connect with C, and B is going to end up alone. So it'll produce AC plus B. AC is always going to be aqueous, and the B is going to end up as a solid. So I know that zinc takes on a +2 charge when it becomes an ion. Nitrate is NO3 minus 1, therefore my compound would look like this. So I'll put that over here. My marker's too big. ZnNO3 2. Leave space for the balance. And then my silver will be left alone. So it turns into a solid. Okay. So now let's see if this equation is balanced. Well, I had to use 2 nitrates on the product side because zinc has a +2 charge, so I needed 2 nitrates. And over here, silver only has a +1 charge, so I only needed 1 nitrate. And so I have to balance the equation by putting a 2 here because I now have 2 nitrates. I now also have 2 silvers. So if I put a 2 over here in front of silver, I have 2 silvers, 2 nitrates, and then I don't need to do anything with the zinc because there's 1 here and 1 here. So that's a balanced single replacement reaction. Let me show you a trick. On the back side of your periodic table, there's something called the activity series. The activity series shows you increasing activity going up through metals and halogens. So let me show you how I knew that these reactions would happen. In my first equation, I put a solid piece of aluminum into a copper nitrate solution. On the activity series, the way that you would read this, aluminum is right here, and copper's down here. If the solid you put in to the aqueous solution is above the metal in the aqueous solution, then the reaction will take place. So let's write that out. If the solid metal placed in the aqueous solution is above the metal from the solution on the activity series, a reaction will take place. If it's not, then the reaction won't take place. So let me give you an example of when a reaction would not occur. All right. So say that I have a piece of lead, and lead is right here, and I put it in a solution of, let's use zinc carbonate. So I have A plus B, and then carbonate would act as C. Well, up here on my activity series, lead is down here, and zinc is way up here. According to this, if the solid metal placed in the aqueous solution, so that would be the lead in this situation, is above the metal from the solution, which would be zinc, then the reaction will take place. Well, if you look here, lead is below zinc. The activity series tells you how reactive a metal will be in an aqueous solution. If it is highly reactive, if the metal is highly reactive, then it is capable of stealing away the anion from the salt. If the metal is less reactive, then it is not capable of stealing the anion away from the salt. So because lead is lower than zinc in this activity series, this reaction will not happen. And by not happen, I mean that the zinc will stay with the carbonates and the lead will end up by itself. So nothing is going to happen in this reaction.